Welcome to this video. We are going to dive into what are called internal thermal gains, the heat that comes from people, lights and equipment inside a building. In this short lesson will clarify what gains are, how they split into two different types, sensible and latent, and how you can quantify them for a building model. Our goal here is to give you a clear, practical understanding. We'll focus on simple definitions, straightforward formulas, and reliable calculations that you can easily use in your own work. Let's lay out our plan for this video. We'll start by defining what internal gains are and breaking them down into their sensible and latent parts. This is a critical distinction and it will set the stage for everything else we focus. Next, we'll go through the three main sources of internal gains: people, lighting, and equipment. For each one, we'll show you exactly how to calculate the heat they add into a space. Finally, we'll introduce the concepts of schedules and diversity to make our calculations more realistic. Because let's face it, not every light is on and not every computer is running all the time. Here's what you will be able to do by the end of this video. First, you'll be able to define internal gains, and more importantly, you'll know how to distinguish between the sensible and latent parts for people, lighting, and equipment. Understanding this separation is key because it allows you to accurately model both temperature and moisture effect. Second, we'll give you the skill to compute internal gains. You'll learn how to take real-world data like unit gains for people, lighting power density, and equipment ratings and turn them into concrete numbers you can use for your calculations. You'll also learn how to interpret these numbers to understand which component has the largest impact on your building's load. Finally, we'll teach you to be a responsible modeler. You'll learn how to document your assumptions, things like occupancy schedules and how often equipment is actually used. This is a critical step because it makes your work transparent, reproducible, and ready for peer review. It's an essential part of a good engineering practice. Before we get into calculations, let's start with a practical question to get you thinking. Imagine a typical office at 3 p.m. on a work day. The occupants are at their desk, the lights are on, and the laptops are humming away. Which of these three sources, the people, the lights, or the equipment, do you think is contributing the most to the cooling load? Your first instinct might be to guess the one that feels hottest or the one that there's the most of, but that's just a guess. In this video, we're going to give you the tools to replace the intuition with a real, defensible calculation. We'll show you how to find the numbers for each source and, most importantly, how to track the sensible and latent heat separately, so your final result is accurate. By the end of this video, you'll know exactly how to rank these internal gains and confidently justify your conclusion. No hand waving or guesswork, just clear, transparent calculations that you can use to make smart design decisions. So let's get started and turn that intuition into cold, hard numbers. So to start this video, let's start with a clear definition. Internal gains are simply the heat and moisture that are generated inside a building by occupants, lights, and equipment. They are different from heat coming in from outside because their sources are internal and can often be controlled by building operations like schedules or equipment use. These gains are split into two crucial components: sensible heat and latent heat. Sensible heat is the heat you can feel, the kind that raises the air temperature. The latent heat, on the other hand, is tied to moisture. It's the energy needed to turn water into vapor, so it increases the humidity in the air. Keeping these two effects separate in our calculations is essential for accurately modeling a building's needs for both temperature control and dehumidification. In a full building load model, internal gains are one of the main components, right alongside heat from windows, walls, and ventilation. During occupied hours, internal gains can be so significant that they actually become the dominant factor in a building's cooling load. The HVAC system must then work to remove this heat and moisture to maintain a comfortable indoor environment. The first and often most dynamic source of internal gains is the people themselves. The heat and moisture generated by people have both sensible and latent components. The sensible part is the heat that raises the air temperature, while the latent part comes from moisture in our breath and perspiration. It's a key factor in cooling loads, and is crucial to keep the two parts separate in your calculations. To compute this, you just need to multiply the number of occupants by the standard heat gains for a given activity level. For example, a person seated at a desk generates a different amount of heat than someone exercising. You can find these values in engineering handbooks. Always be sure to state the activity level you are using. The total gain is driven by a few factors: the person's activity level, what they are wearing, and the schedules that determine when they are in the space. Because people also add a significant amount of moisture, their latent gain can heavily influence the dehumidification needs of the HVAC system. Now that we covered the heat and moisture from people, let's turn our attention to the second major source of internal gains, lighting. Lighting gains are almost entirely sensible, meaning they add to the air temperature but not to the moisture content. We typically calculate this using a lighting power density, LPD, which is the electrical power used for lighting per square meter of floor area. This gives us a simple way to estimate the heat added by lights. The heat from lights can go directly into the occupied space, or it can be pulled into the return plenum, the space above the suspended ceiling where the return air is collected. This depends on the type of fixture, that is, the complete housing unit for a light bulb, and how it's installed. For a recessed fixture, a significant amount of heat is radiated directly to the plenum. This is a good thing for cooling, as the heat is removed by HVAC system before it can affect the occupied room. In contrast, a fixture mounted on the ceiling will radiate most of its heat directly to the room, becoming a direct sensible gain that your cooling system has to handle. The actual heat from lights is heavily influenced by schedules and control strategies. Lights are rarely on at 100% all the time. Daylight sensors can dim lights when there is enough sun, and occupancy sensors can turn them off when the room is empty. You should represent these effects as hourly multipliers on your RPD to ensure your model reflects how the lights are realistically being used. Now, let's move on to our third and final source of internal gains: equipment and plug loads. The heat from the equipment and plug loads is often misunderstood. We'll start with the difference between nameplate power and the actual power used. The nameplate value is the maximum power a device could draw, but it's rarely running at full capacity all the time. Using this number will lead to a significant overestimation of your cooling load. To get a more realistic number, we use two key concepts: diversity and duty cycle. Diversity accounts for the fact that not all the devices are on at the same time. In an office, you may have 50 computers, but it's unlikely all the 50 will be on at once. The duty cycle accounts for a device on-off behavior. A laser printer, for example, is only using significant power when it's actively printing, not while it's in standby mode. By applying these factors, we can get a much more accurate estimate for sensible heat gain from the equipment. Most office equipment, like computers and monitors, produces only sensible heat. However, some devices are exceptions. These things like coffee makers, humidifiers, or steam sterilizers can produce a large amount of latent heat from boiling water or adding moisture into the air. It's important to identify these exceptions and account for their latent contributions to the load to ensure the humidification system is properly sized. Knowing the heat from each source isn't enough. We need to factor in when and how they are used. That brings us to schedules, diversity, and the final summation. Internal gains are not constant, they change by the hour. You can make your model realistic by using schedules for people, lighting, and equipment. These schedules capture simultaneity, the fact that the building's peak occupancy might not happen at the same time as its peak lighting or equipment use. This is the crucial step that turns static nameplate ratings into time-accurate watts for each component. Once you have your hourly gains for people, lighting, and equipment, you can add them to the other heat gains we've discussed, from the envelope, windows, and ventilation. This gives you that total space load. Remember to keep your sensible and latent gains separate. This is how you exactly see which type of heat is driving the load and why your model might predict a peak at a particular time of the day. Finally, always be sure to document your assumptions. This is critical for making your work transparent and defensible. You should report your assumptions for people count, lighting, power density in watts per square, and your equipment. So, to sum everything up, here are the most important things to remember for our discussion on internal gains. First, remember to define internal gains clearly and always keep the sensible and latent parts separate from people, lighting, and equipment. This is crucial for correctly modeling both a space temperature and its humidity. Second, learn how to quantify these gains. Use things like unit gains from people, LPD for lighting, and device ratings for equipment. Then apply realistic hourly schedules to reflect how building actually operates. This is how you transform rough guesses into numbers that you can defend. Finally, report your assumptions and connect your analysis to real-world design decisions. So remember, always to do that, to report your assumptions and connect your analysis to real-world design decisions. By showing how each component contributes to the total load, you can clearly demonstrate why you recommend specific design levers, whether that's installing better lighting control, selecting more efficient equipment, or adjusting ventilation strategies. This is how your analysis directly supports energy and comfort goals. So thank you for watching this video, but remember that this is just a start. To deepen your understanding on internal gains and building modeling, here are a few topics worth exploring. Dive into how the heat from lighting and equipment is actually distributed. You'll find that the design of a light fixture and the ceiling type can significantly change how much of the heat ends up in the occupied room versus the return air plenum. Understanding this split is key to accurately predicting a zone's peak sensible load. Next, investigate the sensible heat ratio. This is the ratio of sensible heat to total heat. Space with the highest ash air needs more cooling, while a space with a low one, meaning more latent heat, requires more dehumidification. Understanding this ratio helps you select the right HVAC equipment and control strategies to manage both temperature and humidity. Finally, learn about advanced diversity modeling and uncertainty analysis. Real-world buildings is variable, and modeling that variability is crucial. By understanding how changes in occupancy, schedules, device use, and the control behavior create uncertainty, you can make more robust and confident recommendations for your building designs. Thanks again for joining us, and I hope to see you in the next video. Bye.